Natural ventilation can remove the residual heat and humidity in the room and ensure airflow and freshness. It is the most economical and effective method for building heat protection. The power of natural ventilation includes thermal pressure and wind pressure. Generally, the two exist at the same time, and the airflow direction is determined according to the pressure difference between the two. Thermal pressure depends on the difference in air density caused by the difference in indoor and outdoor air temperatures, and the height difference between the air inlet and outlet. The outdoor cold air with lower temperature and higher density will enter the room from the lower part of the building, absorb the residential heat and humidity in the room, and the temperature will rise. The density will become smaller and it will be discharged from the upper air outlet. Wind pressure refers to the pressure difference generated by the wind acting on the building. Because the airflow is blocked, the wind speed decreases, the wind pressure increases, and a positive pressure air is formed on the windward side. Due to the airflow around the air is thinned, the wind pressure is reduced and a negative pressure air is formed on the leeward side. When the building is equipped with openings, the airflow will enter the room from the positive pressure air and then exit the room after mixing with the indoor heat and humidity and enter the negative pressure air. Next, let's do an exercise. As can be seen from the conditions and diagrams given in the example, the room has two openings. The openings on the windward side is number 1. The aerodynamic coefficient K is 0.65, and the openings on the lower side of the leeward side is number 2, and the aerodynamic coefficient K is minus 0.55. The height difference between the two openings is 2 meters. Outdoor wind speed is 0.8 meters per second. And the indoor and outdoor air densities are 1.205 kg per cubic meter and 1.27 kg per cubic meter respectively. It is necessary to find the heat pressure and wind pressure and judge the airflow direction. The idea of solving the problem is, first calculate the heat pressure and wind pressure respectively according to the calculation formula of heat pressure and wind pressure, and then judge the airflow direction by comparing the calculation results. If the wind pressure is greater than the heat pressure, the airflow enters the room from the opening 1 on the windward side and flows out from the opening 2 on the leeward side. If the heat pressure is greater than the wind pressure, the airflow flows into the room from the lower opening 2 and flows out from the upper opening 1. The greater the pressure difference between the two, the greater the ventilation. It can be seen from the calculation results that the thermal pressure is greater than the wind pressure. Dynamic pressure difference of natural ventilation is equal to the thermal pressure minus the wind pressure, which is equal to 0.786 Pascal. The outdoor air flows into the room from the lower opening 2 of the leeward side, and then flows from the upper side of the windward side. Opening 1 flows to the outside. It can be seen from this question that when there is only wind pressure, the airflow must enter the room from the windward side and then flow out from the leeward side. When there is only heat pressure, the airflow must enter the room from the low side and then flow out from the upper side. When thermal pressure and wind pressure exist at the same time, the airflow direction is determined according to the maximum value. So, how to determine the ventilation rate? Can the calculation determine the size of the window that needs to be opened? You can try to use the calculation formula of wind pressure to deduce that calculation formula of wind speed, and then deduce the calculation formula of ventilation volume, and use the ventilation volume and wind speed to determine the window air. Wind direction projection angle refers to the angle between the wind projection and the wall normal. The projection angle of the free flow is 0, and the normal ventilation effect is the best, but a large vortex air will be formed behind the building, which will affect the ventilation of the rear buildings. As a result, the building spacing must be greater than 4 times the height of the front building, and the land used will be increased. Using a large wind direction projection angle will lead to a decrease in the wind speed, and the indoor wind speed should be more than 0.3 meters per second. Therefore, it is necessary to comprehensively consider the relationship between the wind direction projection angle and the indoor wind speed, flow field, and the vortex air, and it is necessary considered that a maximum of 45 degrees is acceptable. Origination of the building should first strive for natural ventilation, while taking into account the prevention of solar radiation and summer windstorms. The building spacing is selected according to the wind direction projection angle, which can be combined with the layout of the building groups to reduce the building spacing. The layout of staggeral and oblique has better natural ventilation effect. Building height, length, and depth also have a great impact on natural ventilation. Buildings with different geometric shapes from different vortex airs in different wind directions. The location and air of the opening in the room are related to whether a certain airflow velocity can be obtained in the room and whether the indoor flow field is uniform. Setting the opening in the center is beneficial to the uniform distribution of airflow, and arranging it on one side or setting it on the side wall will easily lead to eddy currents in the room, decrease of wind speed, or even local no wind. The vertical arrangement is also the same. The opening height is closely related to the airflow route. Let's look at a picture. The difference between picture A and picture B is light. Picture A has no overhangs. The position of the inlet and outlet openings is the same, and the center of the air inlet is located above the center line of the house. Compared with picture B, the airflow in picture C is inclined upward and exits the room without passing people's activity air. The ventilation and cooling effect is not good, and the airflow downwards through the people's activity air due to the wind-guiding effect of the overhangs, which can take away the heat and humidity in the activity air. It shows that the height of the air inlet has a great influence on the airflow route, and the height air inlet needs to get the wind downward to effectively cool down. The difference between the AB and CD is light. The center of the air inlet in CD is below the center line of the hose. The same point is light. The position of the air outlet has not changed, and it's still above the center line of the hose. C has no eaves like A. Picture D has the same overhang as picture B. Compared with picture A, the air inlet in picture C is lower, and the airflow also decreases through the active air. The difference between picture D and picture C is that there is an upward wind deflector which raises the airflow. It shows that the lower air inlet is beneficial to cooling in summer, and in winter the upward wind deflector can be set at the position of the air inlet to avoid the invasion of cold wind and achieve the effect of ventilation. This picture shows that when the position of the air inlet is the same but the position of the air outlet is different, the indoor airflow speed also changes. The wind speed of the outlet, the inside of room, and the outlet of the picture is 74%, 48%, and 39% of the outdoor wind speed respectively. The wind speeds at the inlet inside the room and at the outlet are 88%, 55%, and 45% of the outdoor wind speed, respectively, which are 14%, 7%, and 6% lower than those in Fig A, indicating that when the outlet is in the upper part of the room, the wind speed at the inlet, indoor and outlet is lower than the outdoor in the lower part. Let's look at the effect of the room opening air on the indoor flow field. The air of the air inlet and outlet in A and B is the same, but the opening air in B is smaller than that in A. It can be seen that a larger opening has a larger flow field. The inlet of picture D is smaller than the outlet. Since the inflow and outflow air volumes are equivalent, it can be seen from the figure that the outlet flow velocity of the picture C is the largest, and the inlet flow velocity of the picture D is the largest. It is explained that in order to increase the indoor flow rate, the outlet air should be increased. However, when the window air is large enough and the opening width reaches 2/3 of the bay, the wind speed no longer increases significantly with the increase of the opening width. After the opening width exceeds 1.1 meter, the influence on the airflow in the active air becomes smaller. Although the indoor flow field has a great relationship with the entry and exit opening air, when the window to ground ratio exceeds 25%, the flow field is basically no longer affected by the opening air. At the same time, it should be noted that increasing the opening air is good for natural ventilation, but it is not good for blocking solar radiation, and it should increase the heat loss in winter. Therefore, for residential buildings, the window-to-wall ratio is used as a control index, and the allowable range is from 19 to 27%, with an average of about 23%. This picture reflects the wind-guiding effect of overhangs and hanging windows. In picture D, the window position is lower and the ventilation effect is good. In picture A, the overhang of the cornice is too small and the position of the window is higher, which affects the airflow in the room. In picture B, the width of the overhang is increased, and the air can be guided into the room, but the indoor flow field is close to the top and does not pass through the active air. Picture C adopts the inwardly opening hang window on the basis of picture B, which guides the upward airflow to the active air, similar to the ventilation effect in picture D. It shows that the overhangs and hanging windows play a role in guiding the wind. The greening around the building can also play a role in guiding the wind, which can change the airflow field around the building and indoors. Fig A uses greenery to guide the airflow into the opening on the non-windward side. Fig B shows that the height of the tree is reasonable to guide the wind into the room, and vice versa, it will block the wind from entering the room. Based on the above research and analysis results, in order to achieve a better natural ventilation effect, the building layout and section layout should follow the following basic principles. First, the building layout adopts the staggered arrangement. The front is low and the back is high, or the height is increased there by there. Second, correctly choose the combination form of the plan. The main room is arranged on the windward side in summer. The auxiliary room is arranged in the leeward direction, and the ventilation effect is improved by building structure measures, such as hollow partitions, push windows, lattice windows, screen doors, etc. Set open skylights, push skylights, dormer windows, etc. on the roof. Third, use patios, stairwells, etc. to increase the opening air inside the building. Fourth, the arrangement of openings should make the indoor flow field evenly distributed. Fifth, improve doors and windows and other structures which is conducive to guiding, exerting, and adjusting air volume and speed. You can use this principle to analyze design examples and architectural design operations. You can try to make improvements for those with poor natural ventilation. You can also think about how to use natural ventilation to design near-zero energy buildings, how to enhance the natural ventilation effect. What kind of buildings is suitable for natural ventilation? Can natural ventilation be used for smoke extraction in a fire?